All right, hello everyone. So we are going to continue my science Q&A for science and technology Q&A for kids and others. I think our theme for the last couple of weeks has been things in science fiction and to what extent they can be real. And I think we have a few saved up questions which don't seem to be of that type. Okay, well, there's a question here. Maybe I can start on this. What is imaginary about an imaginary number, and what does it? Well, no, yeah. What is it? What is imaginary numbers, and what do they represent, and so on? Well, I think if we're going to talk about that, I have to show you some things. So let's see what I can do there. Let me just arrange this so I can do that. And let me go ahead and share this. Confusing. I have multiple screens here, so there we go. Okay. All right, let's talk about imaginary numbers. Okay. So, as a math topic. So, let's talk about squares of numbers to begin with. So we say something like 2 times 2. On a computer, we represent multiplication by a star. We know 2 times 2 is 4. Great. We say like 6 times 6, 36. These numbers are squares. They're called squares because if we were to have something with 6 boxes along one side and 6 boxes going down, the total number of boxes that we would make in a square will be 36. So we can work out all kinds of squares. So let's make a table, for example, n squared, n going up to 10. So our friendly squares of numbers. So the big question is, it's all well and good to say that 2 times 2 is 4, something like that. But what if we asked about -1? What multiplied by what would be equal to -1? So back long time ago, primarily a chap called Cardano in the 1500s, I think, maybe late 1400s to early 1500s, was trying to figure out the answer to that question. What is, if you multiply what multiplied by what is equal to -1? And so he invented this thing he called I, and I was just supposed to be the square root of -1. So if I say, what's the square root of -1? It'll tell me it's I. It writes it out as a lowercase I, but we type it in as a capital I just because that's the way that it's easiest to have the computer understand what we're talking about. So if we have this thing called I and we say what's I squared, the answer is -1. So we can make a whole system of numbers that work using i's. So for example, we can say something like 2 plus I, and we can say what's 2 plus I squared, and that'll give us an answer. And we can do all sorts of things that we would normally do with ordinary numbers in terms of numbers that contain i's, numbers that contain square roots of -1. So here's a way to think about this. Gosh, we can go in many different directions here. So we can think about a number like 2 plus I, let's say it's 3 plus I. We can think about that as being, so we think about coordinates. We might be saying, let's say we say something like this. We have a bunch of numbers. Let's say we have the numbers 2, 3, 5, 6, for example. We can plot those, and let's do this. Grid lines. Automatic. Okay, so there we plotted those 2 points. So this is plotted, let's just say, hold on a second. Might make it a little clearer. Okay, so we've got these numbers, these points 2, 3, 5, 6. So this is coordinate, x coordinate 2, y coordinate 3, x coordinate 5, y coordinate 6. And that's how we can plot those 2 points in the plane. Well, with complex numbers, we can say when we have a number like 3 plus I, so remember I represents the square root of -1, but it's just this thing that we can think of as just a thing we write down. We don't have to say what its value is. It's just a thing we write down that represents the square root of -1. So similarly, we could say here, we could say something like, call it complex list plot, because these are called complex numbers. We could say 2 plus 3i, t plus 3i, 5 plus 6i. And that, we can represent that the same way. And so this is called representing these numbers in what's called the complex plane, where the horizontal coordinate, the x coordinate, is the real part. That's just the 2, for example. And the vertical coordinate is the imaginary part. That's the thing that's multiplied by the I. So we can think about these complex numbers as being a way of describing numbers that appear in 2 dimensions, numbers that appear in the plane, and so on. So that's and it's, you might ask, is there sort of a generalization of something like complex numbers that works like in 3 dimensions or 4 dimensions or whatever? The answer is it's a little complicated. The idea of having a number that has a real part and an imaginary part is something fairly specific to taking square roots. And there isn't really an analog of that in something like, there's sort of an analog in 4 dimensions, things called quaternions. There's sort of an analog in 8 dimensions, things called octonions, but these get to be wilder and wilder kinds of numbers. But when it comes to complex numbers, we can just think of, there's just a rule that says whenever you see I squared is -1, and if we say, 2 plus 3i multiplied by 5 plus 6i, we can just use standard algebra to multiply this out. It's 2 times 5 plus 3i times 6i. So it's 2 times 5 is 10, and then 3i times 6i is 3 times 6, which I guess is 18. But the I times I is -1, so then we'll get 10 minus 18. And so if we work this out, we should get -8. And then these are the cross terms, which are just, and so if we were just to put x in there instead of I, we'd see this is what we get. Say that, and we say expand that out. We get this. And that's showing us, so the only thing that's different here is x squared we know is equal to -1. So we can replace that x squared by -1. The x is just I here. Let me explain, okay, one more thing about this, and then we'll get off the subject. What was Cardano originally trying to do when he invented complex numbers? So what he was trying to do was he was trying to answer the question to solve an equation. So for example, if we have the equation, let's say we have the equation x squared equals 4. Okay, we can say, what's the solution to that equation? So for what value of x makes x squared equal to 4? And the answer will be either x is +2 or x is -2. Either one of those, multiply them, square them, and we'll get 4. Okay, so now we can look at an equation that says, let's look at another kind of equation. Let's say, let's take a look at the equation. Let's look at an equation x squared plus a times x plus b equals 0. Solve that for x. And let's look at this. Well, let's just look at this for x equals. No, actually, I'll tell you what I'm going to do. Let's do this. Let's make a plot of that function as a function of x from, let's say, -10 to 10. Oops, -10 to 10. And let's manipulate that plot with a going from -4 to 4, b going from -4 to 4. Okay, so for each, so this is for, let's look at what these values are. For a equals -4 and b equals -4, that's what that function x squared plus -4 minus 4x minus 4, that's a plot of that function. So if we want to know for what value of x is that equal to 0? So like solving the equation, x squared plus minus 4x minus 4 equals 0, we can read off the answer here. It's just where this curve crosses the axis. Okay. So now let's change the value. So we can say the answer to that. We could ask it. Let's have it actually show us the answer here. So let's say let's do this. Let's make that plot, and then let's also say n solve of x squared plus ax plus bx plus b equals 0. Solve that for x. Okay, so this is going to show us. Let's make it. Let's put it on top here. Let's just say labeled here. So this is going to show us, hopefully, it's going to show us the answer, right? So this is saying for a is minus 4 and b is minus 4. That's telling us the values of x where that thing x squared plus ax plus b is equal to 0 is x is minus about 8.2 and x is plus 4.8. Okay. So now let's change these values. Okay, so I'm now changing the value of a, and we can see this curve is moving a bit, but we're still getting nice values down here. We're still seeing how that curve crosses this axis. Actually, I'm just going to change one thing here. Just it will be a little easier to see what's going on. Okay, so as we change a, we'll see this curve keeps on crossing the axis. Everything's all good, et cetera, et cetera, et cetera. This is reading off the values where the curve is crossing the axis. Okay, let's now start changing the value of b. Okay, the curve's moving up. It's still crossing the axis. All's good, all's good, all's good. And now eventually, oops, there's a problem. What is the solution? For what values? This is trying to read off for what values of x this curve crosses the axis, but it doesn't cross the axis. There's no value of x on this real line from minus 4 to plus 4 for which this curve crosses the axis. Instead, it's crossing the axis at this complex number value where x is minus 0.3 minus 1.5i. And so what Cardano was looking at, actually, he was looking at cubic equations rather than quadratic equations. And he actually ended up inventing both negative numbers and imaginary numbers at kind of the same time as things you absolutely needed to understand the solutions to cubic equations. We can, just for a little bit more advanced kind of thing, we can take a look at what this thing looks like in the complex plane. Let's see, minus 5i, 5 plus I. So this is a slightly fancier thing. This is looking at, this is for people who know how complex numbers work a little bit more. This is looking at where, actually, you know what? I'm going to make this a 3D complex plot. Okay, so what this is showing is this is a 3D surface that shows the magnitude of the complex number, and the color is the phase of the complex number. When I'm plotting the complex number as a point in 2 dimensions, the magnitude is the distance from the origin to that point, and the phase is the angle between the x-axis and the origin. So as we move, what we'll find here, as we move a and b, we'll move around the positions of those places there. Those are the roots of that equation, and they move around, and we can see them do all kinds of things. Yeah, that what happened there, for people who are into the math of what's going on here, that point, what happened as those things move around, that's the things on the real axis. As they move here, there comes to be get to this critical point, and then the roots go off in the along into the complex plane. So okay, that was a little bit of an elaborate explanation. All right, let's go back here, and let me go back to answering. Sorry, that got a bit mathy. All right, let's demath here, and let's come back, and let me just get to my how do I want to do this? We got a bunch of questions here, so I'm going to try and start addressing those. All right, stop sharing this. Okay, some questions. Okay, well, let's take these from the top here. How can one split atoms and why is it difficult? Okay, so let's talk about what's in an atom. So we have an atom of, let's say, oxygen, nitrogen. Those are two common gases in the air. In the air, we have little molecules which are pairs of oxygen atoms or pairs of nitrogen atoms. They're different kinds of molecules. Water is two hydrogen atoms, one oxygen atom. Okay, what are those atoms? Those atoms have two main parts. They have a bunch of electrons, and they have a nucleus that contains protons and neutrons. The nucleus is the whole atom is very small, but the nucleus is 100,000 times smaller than the atom as a whole. So the nucleus is this lump of protons and neutrons that are in the center of the atom, and which kind of an atom it is, whether it's an atom of hydrogen, whether it's an atom of oxygen, that's determined by how many protons there are in that nucleus. And the protons are, so that there are protons which have a charge +1, and there are neutrons which have no charge. And so typical atoms have roughly the same number of protons and neutrons in them. The usual form of atoms has roughly the same number. There are usually a few more neutrons than protons, particularly when you get to heavier elements in the periodic table. Okay, so what does it mean to split an atom? Well, a lot of times in chemistry, the electrons that are in the atom, they're pulled pretty far away from the nucleus. When you have, for example, chemical bonds, that's all the story of how the electrons get pulled towards one nucleus, away from another nucleus, all those other kinds of things. So the sort of taking the electrons out of an atom is not a big deal. There's a sort of simple, there's an electrical force that holds the electrons into the atom, and lots of things in chemistry, for example, pull the electrons a little bit away from the nuclei in atoms. The real challenge is, what about the nucleus of the atom? How can you, what's involved in, for example, can you take the nucleus of let's say, a uranium atom? Uranium has 92 protons. The typical isotope of uranium, well, the most common isotope is uranium-238, which has a total of 238 protons plus neutrons in its nucleus. So you've got this thing that's a bunch of protons and neutrons stuck together. And the question is, can you split that nucleus apart? Can you turn that uranium nucleus and somehow break it apart and turn it into nuclei of, for example, other kinds of atoms? So, for example, back in the time of alchemy, before modern chemistry, back in like the 1400s and things like this, a big obsession of people was, could you turn lead, which is element number, have to look it up. It's around, let's see, it must be element 80 something, 88 maybe, into gold, which is element number 80. Was there a way of doing that? And that would involve kind of messing around with the nuclei of these atoms. People didn't know that back in the time when they were trying to do alchemy, but nobody figured out how to do that. So, okay, so this question of splitting an atom, it's all about splitting this nucleus. Okay, so the first question is, what holds the nucleus together? So one of the sort of physics facts is, when you have electrically charged things, they can have positive charge, they can have negative charge. Unlike charges attract, like charges repel. So when you have an electron which has a negative charge, -1 charge, and you have a proton which has a +1 charge, they will electrically attract each other. When you have a bunch of protons, they will electrically repel each other because they are all charged +1. So you might ask, how does it succeed in being the case that in the nucleus of an atom, like a uranium atom, you've got 92 protons sitting there in very close proximity, in 1,000 trillionth of a meter across, roughly? You've got you've got 92 protons sitting there all smushed together. So the question is, how does that work? How do they manage to stick together in the nucleus? That was figured out in the 1930s. The answer is, there's a thing called the strong nuclear force. And the strong nuclear force is another kind of force, just like I mentioned, the electrical force between atoms is something that, attracts, unlike the electrical force between particles like electrons and protons and things, that's one kind of force. The strong nuclear force is another kind of force. And the strong nuclear force has a couple of characteristics that are different from electromagnetism, for example, for electrical forces. One feature is that it's very short range. Electromagnetism, there's an inverse square law. When you have things far apart, they will still be having an electrical force of attraction, but the force of attraction will go down like 1 over the square of the distance between the objects. The strong nuclear force has strong interaction between things, but it only has a range of about 1,000 trillionth of a meter. So it's very short range. It's a range comparable to the size of nuclei, actually. But the strong nuclear force in its simplest form has the feature that, unlike electromagnetism, where like things repel and unlike things attract, the strong nuclear force, everything attracts. It's kind of like gravity in that respect. That there's everything is kind of pulled together by the strong nuclear force, at least in its simplest form. Okay, so that's why. So the way nuclei are held together is with the strong nuclear force. What actually is the strong nuclear force? So I have to explain something about electrical forces. The way one thinks about electrical forces in modern physics is in terms of the exchange of photons, or so-called virtual photons. So a photon is what occurs as kind of a particle of light, but there's a virtual version of that. A particle of light, you can emit some light, and you can go, to the other side of the universe, and you can, if nothing was in the way, that piece of light, that photon of light, will go all the way to the other side of the universe. But there's also a notion of what's called a virtual photon, which is a photon that doesn't last very long. It'll be emitted by one thing and absorbed by another thing. And so electrical forces work. One way to think about the way electrical forces work is there's zillions of these virtual photons that are being exchanged between things. And it's like one thing emits a virtual photon, it's sort of pushed a little bit away by that, or pushed, it's moved by emitting that virtual photon, and then virtual photon is sort of thrown to the other thing, and it absorbs it, and it's pushed a little bit by absorbing it or whatever. And it's this exchange of virtual photons that causes the force of attraction or repulsion to occur in electrical forces. Okay, so back in the 1930s, a guy called Hideki Yukawa had this idea that maybe the way the strong nuclear force works is not through the exchange of photons, but through the exchange of a new kind of particle that he called a pion, or pi meson was the original name. And so a pion is a kind of particle, so photons are massless particles, and they have zero mass. Pions have a mass that's about 1/10 the mass of a proton. And it turns out that presence of mass is what makes the strong nuclear force a short-range force. It's because the things that are being exchanged as virtual particles between protons, they're pions, they're virtual pions, and those virtual pions are, because they virtual pions have a mass, it means they can't, the virtual version of them can't go very far, more or less. They unlike the electrical force law, it goes off like 1 over the square of the distance. The corresponding Yukawa potential, the force associated with virtual pion exchange, falls off exponentially with distance. And so that's, so the protons can be attracted to each other, but only so long as they are within about 1,000 trillionth of a meter from each other. If they're further apart, this force that comes from virtual pion exchange disappears. It's infinitesimally small. So when the protons are really close, they're stuck together. When the protons are pulled apart, they just fall apart. Okay, so that's the basic way that nuclei are held together, is by exchange of virtual pions by the strong nuclear force. I'll tell you a couple of other funky things. So there are a whole zoo of particles that get exchanged that cause the strong nuclear force. There's another kind called rho mesons, or rho, which are somewhat heavier than pions. And basically what happens is you take two protons, when they're a certain distance apart, they will be attracting. If you try and squash them together, they will start repelling each other. And that's, in a first approximation, due to the exchange of rho mesons, which have the property that they produce a repulsive force. And back a long time ago, I used to study particle physics, there was a thought that if you push the protons even harder together, they might start attracting again because of the exchange of what was in those days called F mesons. which are even heavier particles, which have even shorter range. And you would have a situation where if you could just squash that nucleus, harder and harder and harder together, suddenly you get, boom, the nucleus would change its structure and you get some new form of matter. So people thought that might occur. It would have been a big deal if it had occurred because it would have let one make all kinds of energy from nuclei, but it turns out that doesn't seem to happen. It doesn't seem to be possible to make kind of compressed nuclei where they're making use of other features beyond the ordinary strong nuclear force to kind of bind the nucleus together more strongly. Okay, but an ordinary nucleus held together by the strong nuclear force. So if you want to break that nucleus apart, how do you do it? Well, you need to kick it really hard, basically. Turns out there are some nuclei that spontaneously fall apart. So in particular, uranium-235, the version of uranium that has 92 protons and 235 minus 92 neutrons, that version, because kind of the protons and neutrons, they're all sort of stuck together, but they probably, because they don't quite stick together, if you have that number of kind of sort of spherical particles or something, they don't quite stick together in a nice way. Probably that's a reasonable way to think about it. The nucleus of uranium-235 is unstable and it falls apart. And so it takes it a while to fall apart. Actually, it takes it on average 1 billion years or more to fall apart. And that means that there were uranium-235s that were created. There were atoms of uranium-235 that were created when the Earth was created 4.5 billion years ago. They're still around. They haven't yet decayed. They haven't yet fallen apart. But if you mine a bunch of uranium, some part of the uranium will be uranium-235, and that uranium will be radioactive, and the form of radioactivity, the form of activity of the nucleus will be, it falls apart. It's so-called spontaneous fission, spontaneous breaking apart of the nucleus. Okay, so you get a bunch of uranium-235, uranium-235 spontaneously falls apart. So in a sense, uranium-235 automatically splits the atom. It splits itself spontaneously, but it does it rather slowly. It does it it takes a typical atom of uranium 1 billion years or more to split apart. So, okay, so now the question is, how do you use that to split other atoms? So the answer is, when the uranium-235 splits apart, it produces a bunch of stuff. It produces 2 kind of other smaller nuclei, and it produces a bunch of neutrons. The neutrons kind of go off, and if one of those neutrons hits another uranium-235 nucleus, it will kick the uranium-235 nucleus hard enough that it will immediately fall apart. It will undergo fission as well. And when that uranium-235 nucleus falls apart, it again will produce neutrons. And eventually you'll get a chain reaction of more uranium-235. So uranium-235 falls apart. The first one spontaneously falls apart. It produces neutrons. Those neutrons hit other uranium-235 nuclei, which would have spontaneously fallen apart in 1 billion years, but now because they're being kicked by this neutron, they fall apart easily, and they then produce more neutrons, and you get this kind of chain reaction going on. Okay, so one of the reasons that doesn't happen in nature is because you don't have big lumps of uranium-235 sitting around in nature. You'll have uranium-235 mixed with uranium-238. Uranium-238 is the isotope of uranium that has a total of 238 protons plus neutrons. And that is stable. That doesn't spontaneously fall apart. So the big challenge in making sort of splitting atoms is to get enough, for example, uranium-235, that you can have that chain reaction occur. And so that's a hard process, and it was done during the Second World War. That was the sort of the big challenge in making, well, it was done actually for, it was a slightly complicated story. I mean, it was done both for nuclear reactors and for nuclear weapons, more or less the same time. Essentially what you have to do is you have to get a bunch of uranium-235. You have to separate it from uranium-238. That's a difficult process. It's done, the most common way it's done these days with centrifuges, where you're basically using it's gas diffusion centrifuges, where what happens is you have a gas of uranium, And it turns out the uranium-238 is sufficiently much heavier than uranium-235 that if you spin the gas around very fast, the uranium-238 will tend to move to the outside more quickly than uranium-235, and that's how you manage to separate the two things. You take the uranium-235, you can use that to make something which will undergo spontaneous fission. You then sort of have enough of it together that it will have enough neutrons that they will go and make more fission of other uranium-235 nuclei, and that's how you generate a nuclear chain reaction, and that's how you sort of split lots of atoms. And once you have, I mean, you can do it in other ways. Basically, what you need is a high energy particle, and for example, you can get lots of high energy neutrons by the splitting apart of uranium-235, for example. But you can get high energy particles in other ways, like with a particle accelerator. And so, for example, the original thing the alchemists wanted to do of turning lead into gold, you could, in principle, bombard lead nuclei with particles, high energy particles, and have them sort of fall apart a bit and make gold. It'd be a very inefficient way to do things and wouldn't work very well, but that's something you can, in principle, do. All right, bit of a long answer there. Let's see. There's a question here, is it possible to make a, okay, there's one question, is it possible to make an arc reactor as an Iron Man? I don't know how that thing is supposed to work, so I don't really know. I don't know the, the question is, can you make a thing that generates just a lot of power and be able to put it in a small volume? Well, we don't know how to do that yet. There might be, I mean, it's just, it's too many ways one might speculate on how to do that. I mean, I think the most, okay, the thing that would be, I've forgotten what's the story in the movie, but the thing, okay, in a normal, the thing that would be a really great source of power is cold fusion. What does that mean? So one way you can make, I've talked about nuclei and how they work, and one of the things about nuclei is if you were to take two nuclei of hydrogen, which are just protons, and you were to somehow to get them to go together hard enough that they would stick, that the strong nuclear force would take over, so the protons will tend to repel each other. So you have to put a lot of force into getting neutrons to protons to get together. But if you can get the protons, if you can stuff them together with enough force, then the strong nuclear force will take over and they will get bound together and they will essentially make a helium nucleus. Okay, so where does that happen? Well, the most important place for us where it happens is inside the sun. The sun is basically powered by the fusion of hydrogen nuclei, fusion of protons, which are the simplest hydrogen nuclei. And how does it work in the sun? Well, in the sun, the temperature of the center of the sun is hydrogen. The sun is mostly made of hydrogen. The hydrogen gas is, that temperature is basically a way of saying that there's a lot of energy in that hydrogen gas. And these molecules of these atoms of hydrogen or hydrogen nuclei are just running around at incredibly high speed. And so at that temperature, when two hydrogen nuclei are going at the speed that corresponds to that temperature and they ram into each other, they will overcome the force of repulsion associated with electrical forces, and they'll end up being pulled in by the strong nuclear force, and they'll make a helium nucleus. And when they get pulled in to make a helium nucleus, they release a bunch of energy. Essentially what's happening is the helium nucleus is bound very tightly together, and the energy that's associated with that binding is kind of released as the sort of strong nuclear force takes over and binds things. There's a binding energy that is released as energy, as kinetic energy of the helium nucleus. So okay, so in the sun, one has hot nuclear fusion, so to speak. One's using temperature, one's using the heat to just give these nuclei enough energy that when they ram into each other, they fuse. Okay, So similarly, people have tried to reproduce that. So in a hydrogen bomb, for example, the way it works is usually the material that's used there is not hydrogen. It's the most common, I think, is lithium deuteride, which is using lithium nuclei and deuterium nuclei, not hydrogen nuclei, but same idea. The thing that you're doing is in that case is in a hydrogen bomb you actually use another. You use essentially another. So confusing thing about nuclei is you generate energy by fusing together things like hydrogen nuclei. You can also make energy by breaking apart things like uranium nuclei. Basically what happens is for light nuclei, fusing them together makes energy. For heavy nuclei, breaking them apart makes energy. The dividing line is iron 56. If you look in the periodic table at iron is the place where anything lighter than iron, when you stuff the nuclei together, it makes energy. Anything heavier than iron, when you break the nuclei apart, it makes energy. So the way it works is in a hydrogen bomb, for example, there is a bomb that is basically made from uranium, plutonium, one of the heavy elements that generates enough heat to be able to push these atoms from a light element like lithium or something together to make them fuse, and that releases even more energy. That's how a so-called hydrogen bomb works. Okay, so the big question, so there's another, people have been trying, okay, when I was a kid, people thought that it was going to be possible to make a nuclear fusion power station, so to speak, where you would take hydrogen gas and you would put it under enough, you would heat it up to the point where the hydrogen nuclei would be running with enough energy that when they ran into each other, they would overcome the force of electrical repulsion, they would be stuck together with a strong nuclear force, and they would release energy. So this was the idea back in the 1950s and 1960s. People were like, this is going to work. It's going to work really soon. We're going to be able to make so-called plasma fusion. Okay, so plasma is something like the solids, liquids, gases. A plasma is sort of the next phase of matter where instead of having ordinary atoms, you have atoms where the electrons have been stripped off. So when you heat an atom up to a high enough temperature, the electrons just get ripped away from the nucleus, and you just get sort of raw nucleus. So what happens in a plasma, what people try to do is to get a plasma of hydrogen, for example, which is just basically a bunch of protons running around. You heat it up. Let's say you heat it up to 10 million degrees centigrade. At that temperature, there's the hydrogen nuclei running around fast enough that if two of them were to crash into each other, they would overcome the electrical force of repulsion. They would get pulled together by the strong nuclear force and nuclear fusion to 10 million degrees centigrade. It has a very strong habit of like, okay, it's like you heat up, I don't know, you have a balloon or something and you heat it up. The air will expand and the balloon will get bigger. The air is just trying to run away very fast because it's been heated up and it's just sort of running faster away. So by the time you get to 10 million degrees, it's running away really fast. So the problem is to confine the plasma, to keep the plasma from running away really fast, so that you've got this thing at 10 million degrees centigrade, and you're able to confine it, to get it stuck in this thing hard enough that you get it enclosed so that the atoms so that the nuclei will run into each other and undergo nuclear fusion. Okay, so that's the idea. So the question is, how do you make a box that will contain hydrogen gas at 10 million degrees centigrade? And the answer is the only known way to do that is to use magnetic fields. So you try and make no material box, the highest temperatures at which things melt are on the order of, I don't know, 6,000 degrees or something. I forget exactly what is it. It's on the order of tungsten is one of the higher temperature things to melt, and it's maybe some things, maybe some composite materials survive at higher temperatures, but by the time you're at 10,000 degrees centigrade, everything's going to be going to have all the bonds that make you a solid, for example, that could make you make a box, they'll all be broken apart. So by the time you're at 10 million degrees centigrade, not a chance. You're not going to be able to make a solid box of anything. So the only option is to make some other kind of box. And conveniently, the protons are charged particles. They're all charged. And so you can use a magnetic field to try and confine those particles. And so what happened is people tried to make all these weird shapes of magnetic fields. They would have magnets in different places. They would try and make a magnetic field. The most common is a thing called tokamak, which is a kind of toroidal magnetic field where you have this gas, and it's the magnets arranged to make a magnetic field that's in the shape of a torus, in the shape of a donut with a hole in it. What you're trying to do is to keep the plasma at 10 million degrees confined inside this tokamak, inside this toroidal magnetic field. Okay, so people thought this was going to be reasonably easy. Turns out it was really hard, because what happens is the hydrogen gas, the magnetic field finds all these weird ways to become unstable. The hydrogen gas finds all these weird ways to get out. It's a bad story. So people have been trying to do so-called magnetic confinement fusion for about 60 years now, a little bit more than 60 years. Still hasn't worked. There's a big project being built in the south of France, a thing called ITER, which is a giant attempt to do plasma confinement fusion. It will succeed in confining a plasma to some extent. And there's been some level of confinement that's been achieved. It's by no means, it's not even close to being able to make like a power station where you're actually getting more energy out from having nuclear fusion occur than you put in, maintaining the magnetic field, maintaining the temperature of the plasma, and so on. Okay, so that's sort of hot nuclear fusion. And that's the thing that everybody believes will work. After all, we have, in the sky every day, we have an example of hot nuclear fusion working in the sun. Okay, so the question is, can you do cold fusion? Can you get hydrogen atoms to fuse together in some way that isn't based on heating them up to a very high temperature to get them to just ram into each other hard enough to overcome the electrical force of repulsion? So back in the, 1980s, I think, maybe early 1990s, there was this experiment reported that was called the cold fusion experiment. So these guys announced that they'd managed to get hydrogen to undergo fusion in a way that didn't involve any high temperatures. And so it was a big sort of excitement. And then people said, oh no, the experiment was done wrong, and the experiment was fake, and it wasn't real. It wasn't, and cold fusion is impossible. So people have believed ever since that time that cold fusion is impossible. Most people have believed that. I personally suspect that there may be a way to do it. And in fact, if you look at the experiment that was done, it was an experiment where palladium, it's an element similar to silver, was used. And one very bizarre feature of palladium is that hydrogen dissolves in palladium. So if you take a piece of palladium, it's a metal, and you start putting hydrogen in it, it'll just absorb tons and tons of hydrogen. And so the hydrogen atoms will just go and get themselves stuck inside the palladium crystal, and they'll just, for whatever reason, palladium just can absorb tons of hydrogen. And so that kind of gives one an idea that maybe in the palladium is somehow acting as some kind of matrix in which you can put lots and lots of hydrogen. Maybe you can put so much hydrogen into this palladium crystal or whatever, that eventually the hydrogens will be able to get close enough that they'll undergo nuclear fusion through the strong nuclear force. Nobody managed to make that work yet, but it's not completely crazily impossible that that could work. And in fact, I wouldn't be surprised if one would not find a way to do cold fusion. It hasn't been proved possible so far, but it's one of these kinds of things where people said, oh, the experiment is wrong, the experiment doesn't work. So it became kind of a bad thing for physicists to study, and so nobody's studying it. There are, by the way, a bunch of companies that are trying to do various forms of fusion using essentially plasma fusion of various kinds, using fusion that based on various other ways of firing particles at each other and things like this. You can get some amount of fusion to happen just by accelerating one proton to ram into another proton hard enough. You can accelerate it just using magnetic fields and things, but you can't get a large number of protons to do that in an easy way. But there's a bunch of companies just nowadays that are trying to do various forms of nuclear fusion as a way to make power. But if you ask me how would an arc reactor, an Iron Man style arc reactor work, I would say cold fusion would be the best bet, but we don't know how to make cold fusion work. So that one's not on the table yet. Okay, question here. The question about, is it possible to make a gravity sphere? I'm not sure what that is. It's probably from a piece of science fiction I don't know. So somebody can explain that. I'll try and talk about it. There's a question about the fifth force. What is it and how does it work? Okay, I can talk about that. So in but by the way, I should say something. We talked about how the strong nuclear force. Okay, so what are the so-called forces of nature? Usually there are 4 of them identified. 2 of them are pretty familiar and 2 of them are somewhat unfamiliar. So the 2 that are familiar are electromagnetism and gravity. So electromagnetism, force of attraction or repulsion between electrically charged things. Gravity, force of attraction between things with mass. Those are 2 long-range forces. The force law goes down like the inverse square, 1 over r squared. Gravity we can think of as due to the exchange of virtual gravitons. Electromagnetism we can think of as the exchange of virtual photons. Okay, there are 2 other forces that are talked about. One is the strong nuclear force that I've been talking about a bunch today. That is more or less due to virtual pion exchange, at least in its simplest form in nuclei. There's sort of a more modern version of that when we think about protons and neutrons and so on. Protons and neutrons are particles that can exist separately on their own, but inside protons and neutrons are quarks and gluons. Gluons are particles exchanged between quarks that bind together quarks. And quarks have the property that, unlike other things, you can't separate quarks to infinity. So I mentioned the law for electromagnetism. The force law goes down like 1 over r squared. As you pull 2 charged particles further apart, the force of attraction between them or force of repulsion between them decreases like the 1 over the square of the distance between them. Okay, you do the same kind of thing with quarks. They are pulled together by virtual gluons being exchanged between them. But with virtual gluon exchange, instead of that going down like an inverse square law, it actually increases. It actually roughly increases linearly with distance. So as you try and pull 2 quarks apart, the force with which they pull themselves together increases as you pull them apart. It's a really weird thing. And roughly the reason that happens is, whereas with electromagnetism, if you have a charged particle and it's going to attract some other charged particle. I mentioned that's due to the exchange of virtual photons. Roughly what's happening is one charged particle you can think of roughly as emitting virtual photons in all directions. But the virtual photons don't interact with each other. So all these virtual photons just stream out from the charged particle. If they meet another charged particle, they get absorbed by that and they cause a force of attraction or repulsion between these particles. And so what's happening is, if you imagine that a certain number of these virtual photons are streaming out from a charged particle in all directions. So if you know the math of this thing, if you have a certain number of, let's say you have some number of these particles that are going out in all directions, the density of these particles will go down like the 1 over the square of the distance. You can think about that. Let's say you've got 1,000 virtual photons all being emitted from this electron or something at the center. Those 1,000 virtual photons, if you say, what is the density of those virtual photons on a sphere of radius r? Well, the surface area of that sphere is 4 pi r squared. And so that means that the density, if you've got 1,000 virtual photons coming out, the density of those will be 1,000 divided by 4 pi r squared. And so that explains kind of why the force law for electromagnetism goes down like the inverse square. It's because the number of virtual photons going in a particular direction will be reduced by the inverse square of the distance that the thing is apart. Okay, so that's how it works with electromagnetism. With so-called color charge, with exchange of gluons between quarks, the big difference between gluons and photons is that gluons are also massless particles, but gluons interact with each other. So photons, they don't intrinsically interact with each other. You have two beams of light. The beams of light, they have things like interference phenomena, but that's for a different reason. But the actual photons of light don't interact. The two beams of light can just pass right through each other. The photons don't interact. Okay, and in full disclosure, when you do full quantum electrodynamics, there is a tiny, there's an effect called light-by-light scattering, which is a tiny effect where photons can interact with each other. But it's a very, very short-range effect where the photons have to hit just dead on. And if people are interested in the physics of it, it's due to the, it's a so-called box Feynman diagram where you have two photons coming in and they produce an electron-positron pair, and that electron-positron pair is then reannihilates and produces two other photons, and that's what leads to light-by-light scattering. But light-by-light scattering is not it's I think 1/r⁸ force associated with light-by-light scattering, but it's really tiny, and it has a tiny coefficient, so it's irrelevant. Light-by-light scattering is not really a thing. So photons, there's no intrinsic interaction between photons. There's no intrinsic law that says that photons can interact with each other. Okay, gluons, completely different story. Gluons intrinsically interact with each other. It's a consequence in physics. Well, fancy math. It's because the group of symmetries, the internal group of symmetries, it's an abelian group in the case of electromagnetism. It's a non-abelian group in the case of the SU3 local gauge invariance of quantum thermodynamics, which is the theory QCD, which is the theory of quarks and gluons. Let me not go down that rabbit hole. That would take me probably 15 minutes to explain what I'm talking about there. But basic bottom line is gluons interact with each other. Photons don't interact with each other, but gluons do interact with each other. Okay, so imagine you have a quark. The quark emits a bunch of gluons. Okay, so if it was emitting photons, the photons would just stream outwards, and the number of photons on a sphere of radius r would go down like 1/r², etc. But the gluons interact with each other. So instead of just streaming outwards all independently, let's say you emitted 1,000 gluons, those gluons are all trying to interact with each other. Those gluons are all attracting each other. And so what happens is that instead of streaming outwards in all directions, the gluons are all clumped together, and they essentially make this sort of string that goes between the quarks. So the gluons, you've got this quark, and the gluons, instead of streaming outwards, they all clump together in this string. And so what's happening is, between these two quarks, you've got this kind of string of interacting gluons, and that string of interacting gluons, instead of the number of gluons that going down like an inverse square law, the number of gluons, well, in that approximation stays constant because they're all clumped together in this kind of string that goes between these two quarks. And that's why the law of, that's sort of a qualitative explanation of what's called quark confinement. The reason that the force law between quarks increases as you go to greater distances, and as a result, these quarks can't be separated, and you don't have any free quarks. They only exist inside protons and neutrons and so on. Now, what really happens is you pull these quarks apart far enough. There's so much energy associated with this gluon, this sort of chain of gluons between them. There's so much energy associated with that you actually start producing other particles purely from energy, from kind of E=mc² type rules. You're actually producing additional particles from that, and so that's what happens. That's in particle physics. When you have high energy particle interactions and you get kind of quarks streaming out from, being kicked out very fast from from an interaction between two high energy protons, you might get jets that are led by a quark that's going out with very high energy. As the quark tries to pull away, it's essentially pulling the string of gluons very hard, and it pulls it so hard that the string of gluons will break in many places, forming additional little strings where there's a quark and an antiquark typically together, that can happily go off and be sort of, those make like in a pion. So in a proton, the main thing that's in a proton is 3 quarks and a bunch of gluons. In a pion, there's a quark and an antiparticle of a quark, and it's a different kind of particle called a meson, that's what's inside pions. Okay, so the strong nuclear force, the sort of classical view of it is it's due to pion exchange. The slightly more modern view of it is it's due to all these things with quarks and gluons, and it's associated with gluon and interactions of gluons. Okay, so we now got three forces. We've got gravity, the weakest force, electromagnetism, the next weakest force. Then we've got the strong nuclear force, or QCD, theory of quarks and gluons. Okay, there is a fourth kind of force, which is traditionally called the weak nuclear force. The weak nuclear force, for a long time, it only did one thing. It only led to nuclear beta decay. So some kinds of nuclei fall apart as a result of emitting electrons. So that happens actually if you have tritium, for example, the nucleus that is an isotope of hydrogen that contains one proton and two neutrons. Tritium is unstable with decays in about 10, 20 years, something like that. What it does to decay is the proton, proton, neutron. It emits an electron together with an antineutrino, and it turns into, what does it turn into? It'll turn into some helium isotope, I think. But in any case, it decays by emitting this electron. And so for a long time, the weak nuclear force, the only thing it did was to lead to nuclear beta decay. Okay, so actually, when I was a kid, it was my favorite sort of particle physics thing was the weak nuclear force. It has a lot of interesting properties. Actually, another thing it does is it leads to the decay of pi mesons. So pions, it's a modern name for a pi meson. Pions decay. There are three kinds of pions: positively charged, negatively charged, and neutral pions. The positive and negatively charged pions decay in about 10 to the minus 8 seconds, 100 millionth of a second, and they decay into usually a muon and a neutrino. And the neutral pion, pi 0, decays into two photons, and it decays in about 10 to the minus 16 seconds. That's a 10,000 trillionth of a second. Neutral pions fall apart into two photons. So the plus and minus pions, pi plus and pi minus, which decay into muons and neutrinos, or sometimes electrons and neutrinos, that decay process is another example of the action of the weak nuclear force. Okay, so what leads to the weak nuclear force being as weak as it is? Well, the answer is the weak nuclear force is also, just like all these other forces, gravity is the exchange of gravitons, electromagnetism is the exchange of photons, the strong nuclear force, in one interpretation, is an exchange of pions, another interpretation is an exchange of gluons, depending on whether you're looking at it at the level of protons or whether you're looking at the level of the quarks that are inside them. The weak nuclear force is due to the exchange of things called W bosons. So W bosons were sort of predicted theoretically, and then were found in the 1980s. 1980s, yeah, 1980s. Right, or was it 70s? No, it must, I think it was either late 70s or early 1980s. So W bosons are another kind of thing that can be exchanged between quarks, between electrons, between a bunch of different kinds of particles. And they lead to another kind of force, but W bosons are so pions are about 1/10 the mass of a proton. W bosons are 80 times the mass of a proton. And so that additional mass makes the weak nuclear force, in a sense, even shorter range than the strong nuclear force, and weaker in some sense than the strong nuclear force. And so that's another kind of force, is the force associated with the exchange of W bosons. There's actually things called Z bosons, which are another type of weak nuclear force. But so those are the four forces: gravity, electromagnetism, the strong nuclear force, or QCD, and the weak nuclear force, associated with W bosons. Okay, so apart from gravity, those other three kinds of forces all kind of work sort of the same way. They are all exchange of a certain kind of particle. It's called a gauge boson, and the mathematics of how they work is quite much the same. And the so-called standard model of particle physics is a model that combines QCD with the weak nuclear force and electromagnetism. Okay, so the question is, are there any other forces that we missed here? Are there any other kinds of particles we could exchange which would lead to forces between things? And so people have had various different theories about what other kinds of particles might exist. None have been found. There are occasionally experiments that say that people have observed things that might occur on different distance scales and things like that, but nothing's ever been found. So right now we have those are the forces that are known. There is an idea called supersymmetry, which leads to some other kinds of forces, but none of them have ever been observed. So it's something that's sort of out there as a thing to study, but it hasn't actually been found. So okay, so that was an answer to that. I got all kinds of, my gosh, so many questions here. There's a question down here I see from Thomas, age 10. Are there more substances or elements that work like palladium for cold fusion? I do not know the answer to that. I think people have claimed that there might be. I don't know. There's a question here from Brian. Where does the energy come from to emit all those virtual gluons? Oh boy, you're having me dive into quantum mechanics and quantum field theory here. Here's how things roughly work. Normally, there's a law of energy conservation. And, well, let's see how to explain this. No, but let me explain it a different way. Normally, something like a photon or a gluon is massless. If you just have a photon, it travels at the speed of light. Because it's massless, it travels at the speed of light. If you can't slow it down, but if you could and you could weigh it, it would have zero mass. Now, okay, this is a little complicated. So in quantum mechanics, there's this thing called the uncertainty principle, which essentially says that, so one of the things it says is, if you try and measure the energy of something, it takes you a certain amount of time to measure that energy accurately. If you're only allowed a very short amount of time to make the measurement, you'll never be able to accurately measure the energy of something. So if the time is short enough, the energy measurement will be uncertain by a certain amount. And in fact, there's the usual uncertainty relation says the amount of difference, the amount of error in energy measurement multiplied by the amount of time you're measuring it is always greater than this constant called h bar, a Planck's constant, a very small number. It's about, well, energy time, it's about 10 to the minus 34 joule seconds. So in other words, if you want it to be uncertain by a whole joule of energy, that you could, if you only made a measurement for 10 to the minus 34 seconds, you would have an uncertainty of 1 joule of energy. Okay, so the way it works is, if you measure only for a very short time, you have an uncertainty about your energy. And so and you also have an uncertainty because energy and mass go together through E equals mc squared. You also have an uncertainty about mass. So what that means is, if you have a photon and you only you're only measuring it for a trillionth of a second, you can't know what its mass is. And so what happens is, a virtual photon is basically a photon whose mass isn't zero, but it only can exist for, let's say, a trillionth of a second. And so the way that the sort of the energy budget works is, energy is conserved. When virtual photons are emitted, energy is conserved, but the mass of the photon isn't the mass you think it is. It's a different mass. In the language of particle physics, never mind. It's in it's kind of a silly word. It's said the photon is off its mass shell. And it's called that because there's a vector that represents the momentum, the form momentum, the energy momentum of the photon. And you say p squared, the energy momentum squared, which kind of represents the surface of a sphere. And it always reminds me of crabs on the half shell and other things that I can't stand eating those things, but that's a different issue. But anyway, the idea is virtual photons don't have to have the ordinary mass of a photon. And that's how kind of the energy budget of emitting virtual photons, virtual gluons, and so on works. Oh boy, somebody is asking here, what is energy? I might be the wrong person to ask that of right now, because we finally have a theory of physics where we can actually answer that question. But it's a slightly long story. All right, let me just look at a couple of other. Okay, there's a question here about fusion again. From Lex here, is helium-3 and moon minerals useful for fusion? I don't know. There was a crazy effort to try and mine helium-3 from the moon, having something to do with fusion. I don't know whether it's really very useful. Helium-3 is a wonderful and bizarre thing. I don't know of other minerals on the moon that are useful. I mean, the fact is, helium, very light element. Our atmosphere has very little, has essentially no helium in it. The reason is that, okay, so at a certain, the force of gravity on the Earth is sufficient that when you have a big enough atom, like oxygen, for example, the force of gravity on the Earth will make oxygen, will keep oxygen kept inside our atmosphere. Hydrogen, because it's a lighter element, it manages to escape the Earth's gravity. On Jupiter, for example, which has much higher gravity than the Earth, hydrogen does not escape. And so the atmosphere of Jupiter is mostly made of hydrogen. On the Earth, the atmosphere of the Earth, the hydrogen and helium, which are very light elements, they escape the Earth's atmosphere. And so we lost, the Earth might have had hydrogen and helium when it was first created 4.5 billion years ago, but they escaped a really long time ago. And so we're just stuck with nitrogen and oxygen in our atmosphere. And a trace amount of heavier things like xenon and so on in our atmosphere. But so on the Earth, there actually is quite a lot of helium in the Earth, but it's trapped under rocks inside the Earth. Trapped presumably from when the Earth was formed. There is a certain amount of helium. Helium is very non-interactive, doesn't form compounds with other elements to speak of, but you can get a fair amount of helium from the Earth. And people sometimes worry that the helium is going to run out in the Earth. I don't think that's right. And so people talked about mining helium from the moon, which seems funky. Helium comes in two primary stable isotopes. Helium has 2 protons in its nucleus. Helium-4, which is the most common type of helium, has 2 protons and 2 neutrons. Helium-3 has 2 protons and 1 neutron. Helium-3 has some wonderful properties. It's a very bizarre kind of thing. Okay, so I'll tell you a little story about helium-3. I at one time had a big kind of, this was in the early 1980s. Okay, a little bit of a story here. So the weak nuclear force, which I was talking about earlier, the weak nuclear force has affects electrons, it affects protons, it affects all kinds of things. But there's one kind of particle which none of the other forces affect, but only the weak nuclear force affects, and that's particles called neutrinos. Neutrinos have almost 0 mass. They seem like they don't have exactly 0 mass, but neutrinos are emitted in nuclear beta decay. They're particles that have very little interaction, because the only interaction they have is through the weak nuclear force. And so neutrinos, for example, the amount of interaction they have increases as their energy increases, but the kinds of low energy neutrinos of the kind that are produced in nuclear reactors, for example, they just go through the Earth. A typical neutrino will just go straight through the Earth. And in fact, there have been a bunch of neat experiments that have been done where neutrinos are like produced in a particle accelerator in Illinois, and they're sent through the Earth, and they're picked up again by detectors in Canada. So neutrinos basically just go through the Earth most of the time. They interact with a very, very low probability. And their only form of interaction is through the weak nuclear force. So, so for example, and by the way, the sun produces neutrinos. There was a big issue years ago because it didn't seem like the sun was producing enough neutrinos, and people were kind of freaking out. Maybe the center of the sun has gone out, because the center of the sun, it takes a photon at the center of the sun 10 million years to get to the surface of the sun. The sun is very opaque. It looks it takes a long time for light to get from the center of the sun to the outside. But neutrinos, because they don't interact very much, neutrinos from the center of the sun, from the place where the sun is hottest in the middle, neutrinos just go straight out to the outside. And so there were experiments done to try and detect neutrinos coming from the sun, and the earliest experiments that were done just didn't see neutrinos. The experiments were done by having deep mines where there aren't other particles, because there's a couple of miles of rock that absorb all the other particles, and the only things that go through those couple of miles of rock are neutrinos. And so then big tanks of well, it used to be liquids, there were also some solid ones that were made, but big detectors that where basically you're looking for that one solitary neutrino out of trillions and trillions of neutrinos, that one solitary neutrino that happened to hit a nucleus just right on, and through the weak nuclear force interacted with that nucleus and produced some and managed to produce an electron, for example, and then you detect the presence of that electron in your detector, and that's and so people built these big detectors for neutrinos, and the big problem was in the earliest such detectors they didn't see anything. Now it's always very suspicious when you look at experiments, difficult physics experiments, and the experiment says I saw nothing, because it's hard to know, was that because there was nothing to see, or was that because you glitched somehow, your experiment wasn't quite set up correctly, and so it just wasn't set up to see something. So it turned out in the case of the solar neutrino experiments, there was a mistake in the experiments, and the neutrinos were there, the sun hasn't gone out, all is well. Later experiments were sensitive to neutrinos that came from slightly more central kinds of reactions in the sun. The earliest experiments were sensitive to an obscure kind of reaction that happens rather infrequently in the sun, and had to be calculated what frequency was, and it was a little bit difficult to calculate. But anyway, so that's the story of neutrinos. Okay, so nuclear reactors produce neutrinos, and they produce them, and the neutrinos from nuclear reactors, just as I mentioned, just go through the Earth. Okay, so one place where there are nuclear reactors is nuclear submarines. So nuclear submarines, they stay under the ocean for long periods of time, and they're powered by nuclear reactors. And they use nuclear reactors because it's a way you don't have to carry a lot of fuel. You just have to carry some nuclear fuel, which is just much more efficient than any other form of fuel. So that means they don't have to go and refuel all the time. Okay, so nuclear reactors. So one of the sort of schemes in the world is, particularly the US and Soviet Union, what was the Soviet Union in those days, had lots of nuclear submarines. And the idea was there are nuclear submarines prowling around under the oceans, and nobody knew where any of them were. And that was sort of an important piece of the story of, don't shoot a nuclear missile at us, because you won't be able to take out our nuclear submarines and they'll come and shoot missiles back at you. But that idea depends on the idea that the nuclear submarines, you can't find where the nuclear submarines are. So one of the issues is the nuclear submarines emit neutrinos. And nuclear submarines, so you've got a nuclear submarine and it's producing neutrinos, but neutrinos are really hard to detect. So most of the time, your nuclear submarines are completely safe. You can't tell where they are, at least not by looking at neutrinos coming from their reactors. Okay, so this is a long, shaggy story, but sometime in the 1980s, I was thinking about, is there a way to make what's called a coherent detector of neutrinos? So when you have an antenna which detects an electromagnetic wave, the way that works, you can have a pretty big antenna, and it's detecting an electromagnetic wave, and sort of the whole antenna is cooperating in detecting that electromagnetic wave, that radio wave, for example. For neutrinos, it seemed like you would never be able to get that kind of coherent neutrino antenna. You would always have to say, oh, the neutrino hit that atom, the neutrino hit that atom. And the chance of that happening is absolutely infinitesimally small. But if you could make a neutrino antenna, you'd have a completely different story. And you would be able to detect neutrinos quite efficiently. And so I've tried to calculate. It turned out the properties of superfluid helium-3 might have led to the possibility of a neutrino antenna, basically. And that I had this difficult problem because I tried to work this out, and I kind of got a fair distance in working it out, and it looked like it was going to work. And it was like, oh my gosh, what do you do? Because you have this thing that you can imagine building, flying in a satellite, that is a coherent detector of neutrinos, which will be a neutrino antenna, which will basically detect the positions of all the nuclear submarines. And so I had this, I was actually pretty happy that this didn't work, but I had this kind of difficult dilemma. What do you do if you know how to do this? And the way it would have been done was using properties of the liquid phase of a very cold version of helium-3 cooled down to a temperature where it becomes a liquid, where it becomes a superfluid, and it has certain weird properties that potentially could allow you to make a neutrino antenna. But perhaps, fortunately, that's one of these sort of ideas that didn't work out. So that was the let's see. All right, I probably should wrap up in a few moments here. Gosh, let's see. Questions about quantum computing and so on. I'm happy to try and answer those another time. Those will be longer questions to answer. Somebody wants to talk about aliens and UFOs and transgenics. I'm happy to talk about that, but that's a longer story. Let's see. Gosh. Boy, there are a lot of interesting questions here. I have to read off some of these questions because I'm really going to enjoy trying to answer these. Wow. Okay. There's a question here okay. All right. This one I can do. If a matter black hole collided with an antimatter black hole of the same mass, what would happen? Okay, that's a really simple answer. There aren't antimatter black holes. There are matter, like electrons and so on. There are always antiparticle versions of electrons. In the case of electrons, they're positrons, things with opposite electric charge. Well, actually, I'm about to say something slightly wrong. Okay, all right. Black holes, which come from collapsed stars that have collapsed under their own gravity, where there's gravity is so strong that even light can't escape from them. Okay, this is kind of interesting. All right, black holes don't come in matter and antimatter versions. Black holes are just, there's a black hole, there's no anti-black hole. And the reason for that is because mass is always positive. There's no version of mass that's negative. There's no negative mass objects that exist. Every particle has a positive mass. Even an anti-electron has a negative electric charge, but it has a positive mass. And so far as we know, and actually this theory of physics of ours kind of explains this, mass is always a positive number. It's never, okay, for ordinary particles and things, it's always a positive number. I mentioned virtual particles. You can have negative mass virtual particles, but they don't last, they can only be temporary. There's also a possibility of negative mass in the universe from dark energy. That's a whole different story. But for ordinary particles, ordinary stuff one deals with, everything has positive mass, even though it can have opposite signs of charge. So for black holes, there is no anti-black hole. It's always just because mass is always positive, it's always a positive mass black hole. Okay, 2 footnotes. One is there are things called white holes, which are believed not to exist in our universe. A black hole, everything falls into a black hole and it's stuck in the black hole. A white hole, everything streams out of the white hole, and it's like a time-reversed black hole. Like everything, if you ran the movie strip in reverse, In a black hole, everything's falling into the black hole. In a white hole, you ran the movie strip in reverse, everything comes out of the white hole. So far as we know, white holes can't exist in our universe. And it's kind of the same reason as eggs don't spontaneously unscramble themselves. Things tend to get more disordered. That turns out to imply that you can have things sort of attracting under gravity, but you can't have this explosion of stuff coming out of a white hole. Okay, the thing where I was stopping myself earlier was the following issue. So there are electrically charged black holes. In the fancy language of relativity, they're so-called Reisner-Nordstrom black holes. Ordinary black holes have a mass. That's all they have. You can also have black holes that have a mass and an electric charge. And so the thing I was wondering is you can have black holes with both a positive electric charge and a negative electric charge. So the question is, what happens if you have two black holes that have opposite signs of charge? Does anything interesting happen? So when you have two black holes, they merge together. The gravitational wave detector a couple of years ago saw the incredible amount of energy that's released when two black holes merge together. In fact, the black holes they saw, they released in about a second as much energy as would be released by having the sun turn all the matter in the sun into pure energy. And there was so much energy that was released and detected as a gravitational wave that gravitational wave, even though that merger of black holes occurred a third of the way across the universe, it was possible to detect that on Earth because so much energy was released all in a second. So the question that I was wondering about is, if you have electric charges and these black holes, and particularly if you have large electric charges, does that affect the merger mechanism for black holes? The answer is, I think, not to a significant extent, unless the electric charge is huge. If the electric charge is huge, you have a bizarre effect called the naked singularity in the black hole. And it is believed that it's not possible for naked singularities to occur from the collapse of stars. Again, many footnotes to that issue. So I think that you can't get a large enough charge in a black hole in our universe. The charge will all get sort of, as the star collapses to form the black hole, it will just splurt out those pieces of charge. They won't be part of the thing that collapses to the black hole, I think. Let's see. Let's see. Oh, there's questions about imaginary numbers. Sorry, I'll talk about that another time if people are interested. There's an interesting question here. Is there anything special about the size of animals on Earth that makes us conscious? Could the weather systems on large planets or galaxies be conscious? I think that's a deeply slippery slope that has to do with the definition of consciousness. I think the answer to that is yes. The weather can have a mind of its own. The problem is that its mind is not a mind that we understand. The only minds that we understand are human-like minds. And so we say, those are human-like minds. Even animals, other than humans, on the Earth, we don't understand their minds enough to know whether we would count as conscious in the human way they're conscious. But that's a longer discussion. So question here, let me just address this a little bit. The force of friction, how is it explained in terms of the four fundamental forces? Friction is sort of happening at a different level. So friction is when you rub two surfaces against each other, they tend to resist being slid against each other. Friction is a force happening at a much longer distance scale than these other forces. Friction is a confusing force. One of the most confusing things about friction is that in ordinary friction, if you push things down, if you have a heavier thing, the frictional force increases roughly linearly with the heaviness of the thing. Or if you push something down, if you push it down twice as hard, the force of friction, the resistance to sliding will be twice as great. And that linearity of friction is not well understood even today. It was discovered at what is it called? It's usually just called the law of friction. But it was discovered in the 1600s, I think, as a sort of mathematical law. It's still not very well understood. But what's happening in friction is, roughly, when you look microscopically at two surfaces, they are like two giant, they're like mountainscapes. except the mountains are at the scale of atoms. And when you're sliding these surfaces against each other, those mountains are kind of sliding on each other. And if you got those mountains, if the surfaces were perfectly, precisely flat, and you weren't in the air, you were in a vacuum in space, for example, and you have these two surfaces and they're perfectly flat, and you put these two surfaces next to each other, well, it turns out they just stick. The atoms in one surface just will stick to the atoms in the other surface, at least if they're the same kinds of atoms, for example. In other words, if you have two crystals of, let's say, silicon or something, and they're perfect crystals, they have perfectly flat faces, and they're in a vacuum, there's no little layer of air in between them, put them together, they'll stick together. There isn't friction, things just stick together, they'll basically form one crystal. In actual materials, they'll tend to have these rough surfaces, and for reasons that are still not particularly well understood, the forces between the atoms in these rough surfaces are such that they're roughly, the friction force is roughly proportional to the normal force, the force with which you push the thing down. And but those forces are due to these little sort of mountainscapes kind of rubbing against each other. And when the mountainscapes get really close, they will try and just link together like perfect crystals will link together in a vacuum. But that force isn't really well understood, and it's a sort of operating at a different scale. It's operating at the scale of many, many atoms rather than at the scale of individual particles. Oh boy, there's a question here from Brian about hard light, as in keeping photons still, like in a lightsaber or something like this. Well, we don't know how to do that with photons. I don't think it's going to work with photons. If, as I mentioned, gluons interact with each other, but gluons interact so strongly with each other that you can't, just like you can't pull quarks apart, you can't pull gluons apart either. So you can't get your full effect lightsaber or something made out of gluons. So we don't know how to do anything like that at this time. Okay, there's a lot of interesting questions here. I probably should, let's see. The question here is it known whether antimatter falls under gravity or doesn't? Yes, that experiment was finally done only about 20 years ago. Somebody got antiprotons and they checked antiprotons fall under gravity. One wasn't absolutely sure of that until that time. People thought antiprotons would fall under gravity and have positive mass, but they weren't absolute. There's two different things. Having positive mass by virtue of the inertia of the proton, that was known. But having positive mass as in the thing falls under gravity, just like an ordinary particle falls under gravity, that wasn't known for sure until about 20 years ago. It was thought, when I was a kid, for example, there was a serious possibility that half the galaxies in the universe might be anti-galaxies. Half the galaxies in the universe might be made of antiprotons and anti-electrons or positrons rather than protons and electrons. And it's actually a very weird thing that there's more matter than antimatter in the universe. Actually, I worked on that back in 40 years ago or something, trying to explain why that was. I think we now do have at least a somewhat reasonable theory for why there's more matter than antimatter in the universe. And it's for very subtle reasons, having to do with things that happened in the universe at less than a trillionth of a second after the beginning of the universe. Basically, there were processes that led to, there were decay, maybe, we don't know this for sure, because it involves some physics theories which we don't actually know are correct. But probably it was due to things that happened some fraction of a trillionth of a second after the beginning of the universe that had a difference between particles and antiparticles that led to a preponderance of matter over antimatter. You know, one of the other mysteries I'll just mention is when you look at molecules like sugar, for example, dextrose. Dextrose, you know, if you know Latin, dexter means right in Latin, right. And that's because the sugar molecule is a molecule where the arrangement of atoms, there are two different forms of the arrangement of atoms. One that one would call right-handed, one that one call left-handed. It's kind of like one is a right-handed screw thread where there's a thing sticking out and there's things sort of curling around that way, and there's also a left-handed version. And if you make sort of sugar by just chemical reactions and things, you get about equal numbers of left and right-handed molecules. But in life, in living systems, we're only right-handed sugars, no left-handed sugars. In fact, it's a big question if you get, I once did this, it's like, does left-handed sugar taste sweet or bitter on your tongue? So I believe some people it tastes sweet and some people it tastes bitter. But right-handed sugar is what all life on Earth has in it. So there's a question: why is it right-handed sugar? Why did life pick right-handed sugar, not left-handed sugar? And why does it have a preference for right or left-handed sugar? So nobody really knows. But here's a bizarre fact: it used to be thought that sort of right and left-handed things would sort of occur equally in physics. But then what was discovered originally in the 1950s was that neutrinos have this strange property that they're always left-handed. Antineutrinos are always right-handed. What does it mean that a neutrino is left-handed? So neutrinos have a spin. They're effectively spinning around, and they travel in a certain direction. And it was thought for a long time neutrinos were massless. They're probably not exactly massless, but if you have a massless particle, then when it's traveling in a certain direction, it can never change its spin. Its spin is always aligned in a certain direction relative to its direction of motion. So neutrinos are always left-handed. So their spin is always arranged in such a way that if that's their direction of motion, then the spin of the neutrino is always arranged in the left-handed way relative to its direction of motion. So that was discovered in the 1950s, that neutrinos, and as a result of that, nuclear beta decay, so-called violated parity, which meant that they made a difference between right and left-handed things. Only left-handed neutrinos get produced. So, okay, so how does that relate to life on Earth? Nobody knows for sure. There's a very recent theory that perhaps cosmic rays, particles that come from the sun, high-energy protons, things like that, they produce things like carbon-14, which is an isotope of carbon, which is unstable, with a lifetime of 1,000 years or so. 1,000 years, is that right? I think so, about 1,000 years. And it undergoes nuclear beta decay. And when it undergoes nuclear beta decay, it has parity violation. It has the things that come out from carbon-14 decay are nuclei that are basically spinning in a definite direction as a result of neutrinos spinning in their left-handed direction. So there's kind of a theory that maybe as a result of cosmic rays in the early Earth, in the atmosphere of the early Earth, produced these basically atoms and photons and things that were polarized, that were spinning in a particular direction, and that led to a slight preponderance of right-handed sugars over left-handed sugars in the sort of atmosphere of the early Earth and in the oceans of the early Earth. And then at some point there was a slight, greater amount of right-handed sugar, and then the first organisms started existing, and they and they replicated themselves, and they kind of went through the sort of chain reaction of replication. And because the right-handed sugar was slightly more likely, as a result of the sort of chain reaction, the right-handed critters won out over the left-handed critters. That's a theory. Nobody knows whether that's actually right, but that's a possible theory for why right-handedness has dominated. Right-handed molecules dominate over left-handed molecules. I mean, right-handedness for humans is a whole different story. I mean, I happen to be left-handed. I'm just waiting for the moment when the 10% of humans who are left-handed really start to complain about all those things in the world that are prejudiced against left-handed people. My least favorite example is the command keys in computer programs, where Command C, Command V, those are left-handed keys on an English keyboard. And that means that if you put your mouse on the left-hand side, if you have a physical mouse on the left-hand side, or even if you use your left hand for a mouse, you can't simultaneously type Command C, Command V and move your mouse around. It's hard luck story for left-handed people. It's kind of a, Bill Gates, founder of Microsoft, happens to be left-handed. And for a long time, he made sure that Windows operating systems sort of were really sort of equal opportunity for left and right-handed folk. But at some point, Command C, Command, we won out, just like those organisms, just like those sugars on the early Earth. It won out, the right-handed thing won out over the left-handed thing. But humans are actually the only species, to my knowledge, who have where the fraction of right and left-handed critters is different. In humans, is about 10% left-handed. But our form of left-handedness, I mean, we have just a huge amount of non-symmetry in our bodies. The heart is on a definite side, and so on. And the brain is arranged in different ways, and so on. And that's why one of my kids actually is left-handed, and she's sort of they're often there are these studies that recruit students for psychological experiments and things, and these studies often say no left-handers, no left-handed people allowed in the study. And the reason is because the arrangement of brain areas in left-handed people tends to be is somewhat uncertain and tends to be different for different people. And so a lot of these studies, particularly ones that use fMRI to actually image things in the brain, they don't want left-handed people because left-handed people's brains are sort of scrambled in some way. Anyway, somebody's asking, do you prefer the name Stephen or Steve or something else? That's a slightly funny story. The name Stephen, my parents, long time ago, sort of would always claim that they were innovative in giving me the name Stephen. Turns out, if you look at the frequency with which first names were used, the name Stephen was becoming super common back when I was born. So not a lot of points there. But the funny thing is, there's a big lump. If you look at the number of Stevens, particularly in the US, Stevens were very common about 60 years ago as a first name. And so, but in the US, the name Stephen was usually shortened to Steve. And so it's kind of an absolutely deterministic thing that if I'm talking to somebody who's like 65 years old or older and they're American, they will always call me Steve. And you really can't even tell them. You say, no, actually, my name is Stephen. They'll just call me Steve. And it's a dead giveaway, so to speak, of kind of it's a very age-dependent thing. Younger people, it's not the case. But so I don't call myself that, but it's sort of amusing that anybody over the age of about 65 and American will call me Steve. Okay. Oh gosh, I've been going much longer than I expected here. So I think I should wrap up here, but these were some really terrific questions, and I will hope to continue next week, and I can start with some of these questions, or please come again and re-ask these questions, and I'll take it from there. So thanks a lot. Hope you found this fun. It's been fun for me. See you.